So please go ahead. The stage is yours. So please go ahead.
Okay, thanks. I will share my screen. Uh, Okay, thanks for the invitation. There will be the two parts of my talk. Yeah, first I will uh, briefly introduce the status of Einstein probe using about 10 minutes. Yeah, then I will focus on our recent work about the EP 240315a. We know recently there are several new types of high energy transients, and they are related to some important science questions. Yeah, but they are usually rare and faint, so it is challenging to find them. So we need the next generation of X-ray monitors with much higher sensitivity and cadence. Uh, with the current non-focusing or World 1 X-ray optics, it is hard to fulfill the requirement of a large field of view and high sensitivity at the same time. One interesting new technology is micropole optics. Yeah, micropole optics is basically a multi-channel plate. On a plate, there are many small square holes or pores. They are in fact very long tubes. If the walls are smooth enough, they can reflect and focus X-rays. Yeah, this structure is similar to that of the eyes of a lobster. So we also call this type of optics as lobster eye optics. Yeah, this type of optics was first proposed by Roger Andra in 1979 and studied by a number of groups, but it is not major until recently. Since 2010, LOC has developed this technology and applied it to Einstein probe. Yeah, this team is led by Professor Shuanan Zhang. It is an ideal optics for wide field X-ray monitor. In principle, its field of view can be as large as 4 pi, with the angular resolution at the level of several arcminutes. Its sensitivity can be better than current X-ray of-sky monitor by at least one order of magnitude. So this is the key technology of Einstein probe. Yeah, ISM probe is a small satellite dedicated to time domain astronomy to monitor the sky in soft X-ray band. It is a mission led by Chinese Academy of Sciences and developed with international collaboration. Its Chinese name is Tianguan, which means the gate of the sky. Actually, we proposed the concept of this mission more than 10 years ago. It is fully funded by the second phase of space science program of Chinese Academy of Sciences, with the collaboration with ESA, MP, and CONES. We used about 6 years to build the satellite, and finally it is launched finally launched this January. Yeah, then we performed some test and calibration in the first 6 months after the launch, and we started the normal science operation from this July. Yeah, there are two main payloads on board the Einstein probe, the Wide Field X-ray Telescope (WFT) and Follow-up X-ray Telescope (FLT). This figure is the configuration of Einstein probe payloads. Yeah, there are 12 modules of WFT around the two FIT modules. WLT adopts the micropole X-ray optics and CMOS detectors. The field of view of each WLT module is about 300 square degrees, so making a total 3,600 square degrees of the field of view. The effective area is about 3 centimeters square at 1 keV, and the energy resolution is 170 keV, around 1 keV. The angle resolution is about 5 arcminutes. Yeah, there are two identical FIT modules with Volt-1 optics and PNCCD detectors. The effective area is about 300 centimeters square at 1 keV of one module, and the energy resolution is 120 eV around at 1 keV. The angular resolution is 24 arcseconds, so it can give much better positions of transients to get the ground telescope. Okay. Oh, okay. The other fact. Okay. During observation of WXT, the onboard computers will process the data in real time. Once a transient is detected, the satellite will slew to point FIT to the transient. And during this process, the information of transients will be sent to ground by BEDO and VHF in real time. Faster TO requests can also be uploaded by a BEDO system within several minutes. Okay, this is the launch video of the example. Okay, this is the first light of WIT. We observed a supernova remnant Cat-A to calibrate its energy resolution. Yeah, this image shows the large field of view of WIT over the galactic center. WIT can monitor the variation of more than 20 sources around the galactic center at the same time. Okay, this is the first light of FIT, observing Puppis A supernova remnant, yeah, to calibrate its energy resolution. Yeah, and this movie shows the footprints of the field of view of WIT in one day. We can cover the all of the night sky in several orbits. We have finished the first round of WIT Our Sky survey. Yeah, this is the Our Sky survey image detected by WIT. Yeah, up to now, WIT has detected more than 6,000 sources, and there are about 60 transients with high significance. This number keeps increasing all the time, and more than 3 sources with low significance. Yeah, normally very few counts of them, about 10 counts, so we can't identify the nature of them. Next, I will show some examples of the transients detected by WIT. This is a fast active transient triggered the onboard processing unit on this September 8th. Yeah, here is the light curve of WIT. Yeah, this source is quite bright, with the peak flux around 10 to minus 9 ergs per second per centimeter square. Yeah, but there is no gamma burst counterpart of this source. Yeah, after the trigger, the satellite immediately slew, and FIT starts the autonomous follow-up observations about 200 seconds after the trigger. Yeah, here is the image of FIT. You can see a bright source within the error circle of WIT, and the positional error of SIT is only about 10 arcsecond. From the light curve of SIT, the source is rapidly fading with some flares in the light curve. Gemini detected the optical counterpart of this source, yeah, but it is too faint to get a redshift. Yeah, here are more examples of the fast activity transients detected by a WLT with diverse shapes in the light curve, and only about 1/3 with gamma ray counterparts. We think they are gamma ray bursts, but we are not clear about the nature of the others. Beside the faster active transients, we also find some transients with a longer duration. Here is one example, EP240408a. It has a short flare with a duration of about 10 seconds. Yeah. But there is a long-lasting persistent X-ray emission before the flare, and its decay is slow with a time zero about 10 days. We didn't find the optical counterpart of this source, and we don't know its nature. Yeah. You can see more details in this paper we published. Yeah, other type of flares we usually detected due to the star flares for different types of stars with the flux from about zero point 0.1 milliCrab to 10 milliCrab. Yeah, WIT can also monitor the long-term variation of known sources, for example, some bright aliens and X-ray binaries. Okay, so you can visit the EP website to see more information of Einstein Prof. Okay, this is the first part of my talk. Okay, next I will talk about the work about EP240315a. Yeah. First, I would like to thank the collaborations. Uh, sorry, the collaborations from EP Science Center, EP Instrument Team, Swift Team, Corners Wind Team, Stargate Team, and other science team members. I should also thank the help of He Gao, Xue Fengwu and Bing Zhang on the theoretical part, and the coordination work of Xue Fengwu, Bing Zhang, and Wei Mingyuan, the PI of EP. Yeah, this work is not possible without their help. Yeah, we already know EP is optimized for faster X-ray transient. Yeah, here I show the sensitivity of WLT, the on-ground one and on-board one. For 1,000 second exposure, the ground sensitivity is better than the on-board one by a factor of 3. For a shorter exposure, the sensitivity is roughly proportional to the inverse of the exposure time. For 100-second exposure, a typical T90 for a long gamma ray burst, the sensitivity is about 10 to minus 10 erg per second per centimeter square. So we utilized EP can detect some faint fast X transient that we don't know before. And we think 0315a is actually one example. On this March 15th, this source triggered the onboard processing unit. About 10 seconds later, EP Science Center received the transient alert, and 10 minutes later, we received the photon list of this source from the VHF network. We thought this source is real and faster and a faster transient, but the EP was still in communication phase at that time, and we just switched our modules 2 weeks before this trigger. So we decided to wait for the full telemetry data and confirm this is a real transient. Yeah, this is the main reason for the large latency between the trigger and the detection GCN. But fortunately, the optical detection was still in time. VLT determined the spectroscopy redshift to be about 4.9. We also performed the FLT follow-up observations about 42 hours after the trigger. Here I show the WLT image, light curve, and the spectrum of this source. You can see this source is quite bright. You can even see the cross arm of this source, which is the feature of MPO. Yeah, actually, this source is detected during a long FIT of the calibration of VLAN SNR. The left is the full image of CMOS chip that covered this source. The right is the light curve of WLT. You can see many pulses here. T90 of WLT is about 1,000 seconds. Bat and corner wind also detected this source in this narrow interval, about 40 seconds. We have fitted the integrated FIT, WIT spectrum using an absorbed power law and found there is some intrinsic absorption with somewhat large error. We selected some epochs in the light curve and fit the spectra separately. Yeah, there is a moderate spectral evolution during the Prof emission phase. The spectrum is harder in the interval with gamma ray detection. Yeah, I think this figure is very important for this source. The WLT observation clearly shows that the central engine has already begun intense activity long before the detection of gamma rays. The X-ray duration is longer than the gamma ray one by a factor of 25. For the 40-second interval detected by BAT and corner wind, we performed joint fitting. The spectral can be well described by a cutoff power law with E peak around 280 keV. So the X-ray is likely to have a common orange with the gamma rays associated with the internal dissipation process. If we put this source onto the Amati relation, it is located at the 1 sigma boundary and at the higher end of high redshift GRBs. The duration in X-ray band is much longer than gamma ray band, but the affluence in the energy unit of gamma ray band is still larger than that of X-ray band by one order of magnitude. And if we perform a cross-correlation analysis, there is a positive lag of 11 seconds between the X-ray and the gamma ray light curves. Yeah. Due to the importance of this source, we conduct a multi-wavelength observation campaign. The light curve can be well described by a simple forward shock model, and there is no jet break detected when we submitted this paper, and we can't get strict constraints on the parameters since the data points are still limited. Here are two WLT detections much higher than the model prediction, which we think are due to the late time activation of the central engine. And if we include a rebrightening signature at about 3.5 day, the fitting will be significantly improved. This feature could be due to the reactivation of the central engine or a complex jet structure. The radial flux was still increasing when we submit this paper. So the detailed radial result is reported in another paper. And with the late radial observations, we detect the jet break in the radial light curve. Okay, next let us discuss some comparison and prospects. Yeah, there are some gamma ray bursts detected in X-ray. The left is one example detected by the wide field camera on board Babel 6. It detected two precursors in X-ray preceding the gamma ray pulses by about 30 seconds. Yeah, but they are not isolated from the main pulse. And for this source, the difference between the T0 in X-ray and gamma ray band is only about 30 seconds. But for O315A, the difference is 300 seconds, longer than this one by a factor of 10. The right is another example detected by XRT on board Swift. That was triggered by the precursor of this source. So XRT detected the entire Prof emission phase. The pulses in X-ray band are broader than that in gamma ray pulses, but the profiles are similar, and there is no isolated pulses in the X-ray that is not detected in gamma ray band. O315A was outside the coated field of view of BET in some epochs. The extrapolated flux from WXT band are consistent with the upper limit of BET and Cornus wind. Yeah, if this source was at the center of the field of view of BET, it could detect some bright epochs, yeah, with the flux higher than 2 times 10 to minus 9 across per centimeter square per second. Yeah, just as other GRBs in the BET catalog. Yeah, but WLT can detect fainter pulses to the flux level of 10 to minus 10. So we expected there will be more examples like low O315A that some pulses or the entire event can't be detected in gamma ray band. You already know WLT has detected a more fast X-ray transient since that, and we are compiling a catalog of them. I would like to show one example similar to O315A. Yeah, we detected this source on this October 26. Yeah, this source also triggered the BET. In the WIT light curve, there are some pulses before and after the BET detection, yeah, which is similar to the situation of O315A. If we compare the light curve of O315A with other high redshift gamma ray bursts, we found it is much longer than other high redshift ones, and its peak flux is also at the faint end. If we put this source to a higher redshift, its significance will decrease, but it still can be well detected, even at the redshift of 7.5. The right is a simulated light curve of WT and FFT at a redshift of 7.5. Yeah, the positional error of WT is only 2 arcminutes. Yeah, it is not easy to identify the optical counterparts in some situation. We have enabled the autonomous follow-up observations of FFT after the normal sense operation. It will get the early emission phase of the source like O315A. The positional error of FFT is only about 10 arcseconds, which will increase the probability of redshift measurement. Yeah, that is very important for future high redshift sources. Summary. WLT captured the early central engine activations and extended the late engine activity through a continuous detection. This result poses challenges to conventional definitions only using gamma ray data. Yeah, for example, if the T90 of X-ray is much longer than the gamma ray ones, which one we should use? And how to select T0 if the X-ray detection significantly precedes the gamma ray detection. Yeah, this will also impact the value of temporal slope in the light curve. This faint high redshift source showed great potential of Einstein probe to study the early universe where gamma ray burst, and there are already more faster X-ray transients detected by EP. You should know some of them by distant circulars and notices. At present, the issue of WIT descent notice is fully automatically. EP Sensor Center has decreased the latency between the trigger and the descent notice from about 1 day to 5 minutes. And you can subscribe to EP descent notice at this web link. Okay, I will stop here and take your questions. Thank you.
Thank you very much. So questions, please.
I do have one. Well, first of all, thanks for the very nice talk, very interesting. You just mentioned the differences between, for example, T19 and possibly T0 in X-rays and gamma rays. I was wondering whether you already started to look for possible delays between the X-rays and the gamma rays. So try to populate better, let's say, what is the intrinsic probably difference in time between the emissions of X-rays and gamma rays. If you have a systematic simultaneous observations, that would be probably very nice.
Yeah, I think that is our future work. For this source, we perform the cross correlation between the light curve of X-ray band and the gamma ray band, and there is a positive positive lag at about 11 seconds. And for some source, for example, this source, the lag is not so significant. So I think this lag will change with different source. Yeah, and we are compiling a catalog for the fast X-ray transient, and we will compare the light curve in gamma ray band if there is a gamma ray counterpart to systematically see the possible time lag. Yeah.
Thanks. So you probably mentioned, but I forgot it. So what's the number of gamma ray bars so far seen by Einstein probe?
For the fast X-ray transient, the total number is about 60, but only 1/3 of them we found a gamma ray counterpart.
Okay. Okay. Okay, thanks.
Okay. More questions, please.
I have a question. So, thank you very much for interesting talk. How much these fast X-ray transients are different from X-ray flashes which were observed by or discovered by Beppo-Sachs and observed by other missions in the past? Do you think these are the same objects, or we are observing something new?
Yeah, for the gamma ray burst detected by Beppo-Sachs, I think several tens of gamma ray bursts already detected by Beppo-Sachs. So if we only talking about the gamma ray burst in X-ray, this is not very new. Here we would like to emphasize is the isolated. Let me see this. Here I would like to emphasize is the isolated pulses before the gamma ray detection.
If I may make a comment.
Okay.
Hello, I'm Cristiano Vidorsi, so thanks for the nice talk. Yes, Beppo-Sachs wide field camera detected about 60 events that were gamma ray bursts detected both X-rays and gamma rays. Actually, also in the wide field camera detected gamma ray burst, we saw some activity in the X-rays that preceded the major gamma ray activity that then we saw with the gamma ray burst monitor in the gamma ray band. So So this is something which is reminiscent with of what wide field camera on board Bepossax saw. And also, in particular, I was wondering about the events that there are also the so-called X-ray rich events. So gamma ray bursts that were seen just with the wide field cameras and no counterpart in the gamma ray monitor. So also this seems to be, I don't know to which extent the two populations, so the one seen by Einstein probe and the one that was seen by the wide field camera are similar. But I was wondering whether, so all the transients that you see just in the X-rays, and so you cannot say whether they are gamma ray bursts as we know them, to which extent they are similar to what Bepossax and also HT2 classified at the time as X-ray rich events. Thank you.
Yeah, thanks for your comments. Yes, there some sources detected by WLT could be attributed to the X-ray flash. Yeah, similar to the events detected by Bepossax and HT2. But for some events, we don't have the gamma ray counterpart. For the conventional definition of X-ray rich events, detected by HT2, they use some ratio between different energy bands to define the X-ray rich. Yeah, but for WLT, the energy band is relatively narrow, only from 0.5 to 4 keV. So we are thinking about to define some new quantities to codify the shape of the spectrum.
Okay, thank you. Any other questions? No more questions? Okay, Yuan, thank you so much for making the presentation on the Einstein probe advances. Thank you for the very interesting talk. It was a pleasure to have you as a speaker. Thank you all very much. And
okay, thanks. Yeah.
see you after the New Year break.
Yeah.